Hello, class. This is Mr. Hart. And this podcast, we want to continue our discussion of waves. And we're going to stop talking about sound waves for a little bit, and we're going to move on to light waves. And one of the big ideas of light waves is understanding what types of light there are. And that's a big, long phrase that we call the electromagnetic spectrum. Okay, so we'll get into that in just a second, but let's start with, really simply, a question of what is light. Okay, now, we've all experienced, seeing light all of our lives. We know now that's a wave that doesn't travel through a medium, but how does light actually propagate? How does it move? Okay. Well, we like to call it an electromagnetic wave. Okay. And if you remember our discussion about electromagnetism a little while back, we talked a lot about how electricity and magnetism can generate fields for one another. Okay, so light is an electromagnetic wave, meaning it's a field of electricity and magnetism that moves back and forth. Okay, basically the electric field generates the magnetic field, and the magnetic field generates the electric field. So they sustain one another as they make one another. Okay, so we got this constant battle that's occurring between the two fields as they propagate together. And anyways, the point is it's a phenomenon of electromagnetism. Okay, and that is what generates the light. Okay, if you don't understand that, it's not a big deal. If you do, great. It's really cool to think about the fact that electricity and magnetism can propagate together and make the light wave. Okay, but regardless, we need to understand what are some of the applications that come from these light waves, the fact that they're electromagnetic waves. Okay, and one of the big things we need to understand is this spectrum, because there's all these different wavelengths and frequencies we can have for light waves, and that's what we call the electromagnetic spectrum. It's basically this list or range of all the wavelengths and frequencies of which we can have this electromagnetic radiation or this light that can exist. Okay, you've probably heard of some of them. There's radio waves, there's microwaves, there's infrared, there's visible light, there's ultraviolet, there's X-rays. Okay, things that we probably don't associate with each other. Okay, an X-ray and a radio, right? That's not things we like to think of as being the same type of stuff, but they're both made from or come from electromagnetic waves. Okay, and they're just on different sides of a spectrum. Okay, so the spectrum looks like this. Okay, so we start with the lowest possible wavelength. Okay, or longest possible wavelength, lowest frequency. Okay, so on the very left side of the spectrum, we have really long, wavelengths, really low frequencies. They don't oscillate very fast, and that's the radio type waves. And then as we go to the right, we get, faster and faster frequencies. Okay, shorter and shorter wavelengths, and you get really, really, really high energy. Okay, and we get gamma rays over here and X-rays. Okay, and if this is on a log scale, so it's not 2 scale. You got 10 to the third meters right here. That's 1,000 meters long, a kilometer, almost a mile long wave. And then over here you got 10 to the minus 12th, which is smaller than an atom. Okay, so this definitely is not to scale, but as the wavelengths range between these two ends of the spectrum, we get different properties and different types of waves. Okay, down here you can see kind of the things you would be able to see with that type of light, or type of wave. So radio waves will hit into buildings. Microwaves and lower radio waves are about the size of humans. Okay, but you get down to the size of atoms, the size of nuclei, and that type of thing. Okay, and so this is the spectrum. There's a lot of stuff that can be absorbed here. So I'm just going to point out specifically what I want you to write down and understand. Okay. So this is the spectrum as I like to draw it. Okay. So there's 7 main types of electromagnetic radiation that you need to know. Okay. There's radio waves, microwaves, infrared, visible, ultraviolet, X-ray, and gamma. Okay, so please write those down somewhere so that you know which types there are and which order they're in. Okay, this is their order from longest wavelength to shortest wavelength. Okay, and then the visible spectrum is the part that we can see with our eyes. Okay, we can't see infrared, we can't see ultraviolet or any of these other types of rays, but of the visible spectrum, we can see the colors. Okay, and you hopefully know the colors from kindergarten. There's red, orange, yellow, green, blue, indigo, and violet. But specifically, that is the order of their wavelengths. Red being the longest, violet being the shortest. So you'll often hear people say Roy G. Biv. Okay, that just is a way for you to remember the order they are set in. Okay, so make sure you know the order of the types and the order of the colors for the visible spectrum. Okay, so again, you can kind of imagine I'm just taking like a small snippet of the spectrum, the visible spectrum, and I'm expanding it for you so you can see all the different colors. Okay, so you should know that on the very left side of the spectrum, we have lower frequencies, longer wavelengths, and lower energy. And then moving to the right on the spectrum, we have higher frequencies, shorter wavelengths, and higher energies. Okay, so this is the information I need you to know. You need to know what's in the spectrum and their order, and you need to know that you start on the low energy side on this side and go to the high energy side moving to the right. Okay, so write this down. Make sure you kind of have this order down. Use it as a reference, okay, as you're going through the homework, but you should have this memorized by the end of the unit. Okay. All right, so that's the spectrum, but let's talk about why having all these different possible values of light is so important and why it's so cool. Okay, let's start on the very far left, the radio waves. Okay, now you probably have heard of radio, right? You know that you can get radio waves in your car. Okay, you can listen to radio wherever you're at, right? Because they propagate really far. They can go through buildings. They can go through a whole lot of stuff, right? So radio waves are really long, low energy, and low frequency, right? You probably have tuned your radio to, I know a big station right now is like 97.9 FM, okay? That's like the now hit station, I think. But what does that mean when you go to 97.9 FM, okay? Well, that's a frequency measurement, okay? That means that the station exists at a certain offset and certain frequency around 97.9 megahertz. Okay, so it's actually describing how quickly that wave is moving. So one thing to keep in mind is we think of radio as the slowest and lowest frequency, longest wavelength, but it's still moving back and forth 97.9 million times a second. Like they're still moving fast, right? It's still light. It still has to travel at the speed of light. So even though it's really long, it's still moving it's oscillating back and forth pretty dang fast compared to what we're used to seeing. Okay, so we think of it as being really slow. It's still moving the speed of light. It still has a really high frequency. Okay, but radio waves are nice because they don't interact with most objects on our scale, which is why they propagate so well. They can go through buildings because they don't interact with the walls. They can travel through the atmosphere really well because they don't interact with the air. They can rebound off clouds and things like that. So you can get radio waves to travel really, really far. I'm actually ham radio licensed, and there's a record, I'm pretty sure, that they've gone a radio wave to get from, I think it was in California to like Morocco or something crazy. They got over the ocean and into Africa. So these waves, if you can send them right and you get them just right, you can get them going super far. Okay, they can travel around the earth. They can travel through the whole valley, right? I mean, they can. Their benefit is they don't interact with anything. They can travel as far as we need them to. Another important wave that we don't really see, right, that we don't interact with a lot, is microwaves. Okay, a little bit shorter wavelength. Okay, a little bit higher frequency. You probably heard of the microwave because you probably have a microwave oven. Okay, now the thing that is confusing is microwaves really don't have a whole lot of energy, but they're used to heat your food. Okay, the reason being is that the microwave, there's a certain wavelength that microwaves actually will interact with water. And actually, I just looked it up. The exact frequency that they send through on a microwave oven is 2,450 megahertz. Okay. So that's what they send through the oven. Then that just happens to be the wavelength that water will have its resonant frequency at. So the water starts to shake back and forth really fast, which generates heat. Okay, so if you have really dry food and you try to microwave it, it usually doesn't get very hot because there's no water in there. Okay, so microwave oven works specifically because it's sending a very specific microwave. It's that exact frequency that moves the water back and forth really fast, and that's what heats up your food. Okay, so very useful application of that wave. Another common wave that you'll see in the microwave spectrum or subset is like communications, Bluetooth, Wi-Fi, your cell phones. They all communicate with each other on the microwave spectrum. Okay, again, usually, other than the very specific case of an oven, low energy. Okay, it's a really low energy, so it doesn't cause a lot of harm to humans or anything. They've done studies, and most people have found that there's really nothing that happens to any human cells or anything when you have a cell phone or a Bluetooth device near you. Okay, so they're nice. They don't cause harm to us. They can communicate, at light speed, right? So they can send a light wave. They can go through walls still. They don't interact with a lot of the particles. They don't interact with the air. Okay, and they can travel quite a far distance. And so we use the microwaves a lot for kind of our modern communication, these wireless devices that are synced with one another. Okay. Another common wave that's less commonly used nowadays because of cell phones and things like that, but is infrared. So infrared waves were used a lot for communication kind of in the late 90s. If you have kind of just a standard remote, it probably has an infrared communication device on it. So it sends an infrared wave to the receiver, and the receiver uses that infrared wave to know what to do based on what button you clicked. Okay, but infrared has one thing that isn't very useful, or is kind of why it's died off. Infrared does interact with objects. So if you stuck your remote and you stuck your hand right in front of your remote, you wouldn't be able to communicate with your TV because it can interact with your hand, it can interact with other things. It's on that scale where it starts to interact with a lot of objects, and so it's kind of line of sight. Okay, if you ever had like a Wii console, Nintendo Wii console, right, where you could use the motion controls were infrared, right? You had that little bar that you set on your TV, and you'd had to point your remote at your TV in order for it to know where your remote was. Okay, but again, it's line of sight. If something's in the way, then it can't get through. Okay, so that's why infrared's not used as commonly nowadays, because it was line of sight based. But we still use it for some communications. We still use it for most TV remotes because it's cheaper. But there's other applications of infrared. Okay, a lot of animals, for example, can detect things in infrared. They can see in infrared. Okay, I believe a lot of snakes, for example, can see in infrared. This is an example of what a mouse might look like in the infrared. Okay, which is nice because we emit heat. Most animals and mammals emit heat in the infrared. So that means even at nighttime, these species can see things at night because they see the infrared, not just the visible light. Okay, so pretty cool. Still a lot of use in obviously just nature, but we don't use it for communications as much anymore. Okay, then we get to visible light, which hopefully you're familiar with it because you see it every day. Okay, you probably have seen a rainbow, which is an indication of the different colors that you can see. Again, it interacts with pretty much every object we can see, right? That's why we can see it. It's kind of circular reasoning there. But anyways, the point is, obviously, visible light can't get through anything that you can't see through, right? If you could get through it, you could see through it. So visible light can get through glass, which is why you can see through glass. It can't get through most other objects, which is why you can't see through most other objects. Okay, but this is the wavelength and frequency that your eyes can detect. Okay, that's what your corneas are, synced to. You actually have 3 corneas to kind of be more sensitive to certain types of visible light. People that are colorblind usually only have 2 functioning ones, which makes it harder for them to distinguish between different colors. Okay, but I'm not going to focus too much on this because you'll probably talk more about the biology of your eyes in biology class and anatomy and stuff like that. But visible light, that's the colors we can see. Okay. Moving on, there's ultraviolet lights. They're very high energy, okay, can be very dangerous. If you've ever been to like a black light dance, or you get those stamps at like Lagoon or other places where it glows under a black light, okay, they call them black lights, but they're actually low energy ultraviolet lights, okay. They can make certain objects glow. So ultraviolet can be really dangerous and harmful if it's higher energy. For example, the sun emits a lot of ultraviolet, and the reason we wear sunscreen is because the ultraviolet waves is what causes the sunburns and skin cancer and stuff like that. You probably have seen a UV rating on a sunscreen. When you get like SPF 30, that means it's blocking 30 waves for every one that gets in. Okay, but it's the UV that is the dangerous part. So ultraviolet's not used a whole lot by us because it's generally more of a dangerous wave. Can cause a lot of harm to cells and things like that. Okay. And then moving on, there's X-rays. Also very dangerous if not controlled, but it's very useful because X-rays go through skin, but not through bone, which is why we use X-rays machines at the dentist and the doctor, okay? Because it will go through your skin cells but not go through the bone, which is why we can detect them, okay? And so using the X-ray machine, they send a very small amount, low energy, okay, just enough to see the bones and things like that and get some information. Okay, which is a cool application. Not a whole lot of application in nature because, again, very high energy that's not generated a whole lot. But it's just a very high frequency wave. And then the last one we're not really going to even talk about, it's a gamma ray. You'll see it a lot on the atomic scale. If you take chemistry, you'll learn about the different types of radiation and stuff like that. But it's just a super high energy wave that we never use because it can cause lots of harm. Okay. But that's the spectrum. So going back to this, that's from the very, very big all the way down to the ridiculously small. Okay, and we can use them and use them for different applications. We can see them in nature in different aspects. Okay, but understanding and controlling these waves has been huge for communication for sure. Okay, just understanding radio versus microwave versus infrared, being able to manipulate waves to use for our benefit to communicate with each other is absolutely huge. Well, I hope you hopefully have learned a lot about the different types of light. I hope you'll understand what they're used for and kind of a little bit of the history of where they come from. But that's it for today. So just make sure you do the homework on the E&M spectrum. There's two sides to it. Just make sure you do both sides. But hopefully that all made sense. Let me know if you have any questions, and thank you for watching.